Okay, so last week we watched the brain pop video where we were kind of introduced to this idea of the electromagnetic spectrum and the different types of light that there are. There's only a little tiny part of it that we can actually see. There's lots of other different types of light that our eyes cannot pick up on. But any type of energy that we have that we consider to be light is also called electromagnetic radiation. And it's a type of energy that travels through space in the form of waves. And it's composed of oscillating electric. Can anyone guess what our second one will be? What other type of field? Magnetic, good. What does oscillating mean? Yeah, like back and forth kind of thing. If you have an oscillating fan, that's one of the ones that goes side to side, back and forth. So this wave of energy is oscillating back and forth between electric and magnetic fields. And the spectrum can be arranged due to frequency, wavelength, or energy. And whatever you arrange it due to one, the others kind of fall into place. This one is arranged from long wavelength, 10 kilometers, all the way to a picometer, which is 1 times 10 to the negative 12th of a meter. So this is a very short wavelength over here on the other side. And when we talk about wavelengths, it's probably good to know different parts of a wave. So let's actually skip down to the bottom, and then we'll come back to this here in a second. When we look at a wave, can y'all think of what we might call the very top part of a wave? And you can kind of think about waves in the ocean also. It's going to start with a C. Crest. So the crest is the top of the wave, and then the bottom of our wave is called a trough, like a horse trough. So whenever we have a wavelength, we can write a Greek letter called lambda. It looks kind of like an upside down Y. But it's the distance between two consecutive crests or troughs. So the distance from one top to the next or one bottom to the next. So this guy right here is going to be a wavelength from top to top. And this one down here is also a wavelength from bottom to bottom. Those are the same distances. And anytime we talk about wavelength, that's what we're measuring. And when we look and count how many waves go past every second, and by a wave, we're talking about a wavelength. If we count how many go by every single second, that's going to be the frequency of the wave. So frequency is the number of waves or cycles per second. And so our unit for that would be per second. That'd be the same as 1 over seconds. And that's also the same mathematically as if you write seconds to the negative first. Anytime you have something raised to the negative first power, it's the same as 1 over whatever that is. And there's another unit that we could use that actually means the exact same thing and that you might have heard of before. That's going to be hertz. You put HZ for the abbreviation, but that's the same thing as seconds to the negative first power. Okay? So then the next part of a wave we're going to look at is the amplitude. The amplitude is the height of the wave from its rest position. So rest is going to be this little dotted line that goes to the center. That's the middle of your wave. So if you start from the middle and go up to the top of a crest, that's an amplitude. Or if you start at the middle and you go down to the bottom of a trough, that's also an amplitude. They would be the same distance. Okay? And then all waves are going to travel at the same speed. It doesn't matter what the wavelength is, what the frequency is, how much energy it has. They're all going to go at the speed of light. Light will travel at the speed of light. And we're going to use C for our letter for that. We're going to cross that other part out. And if you've ever heard of the equation E equals mc squared, that C squared part is the speed of light squared. And if it's in a vacuum, that value is going to be 3.00 times 10 to the 8th meters per second. If you have miles per second you're trying to figure out, that's what I have on the little filing cabinet over here. It's 186,000 miles per second about. So I can go very far, very quickly, very fast speed. If you went ahead and wrote this out, if we moved our decimal to the right 8 places, it would be 300 million meters every single second. So that's how fast that light is traveling at. So when we go back up and we look at our spectrum that we have here, It is arranged from long wavelength to short wavelength, which also means that it's arranged from low frequency to high frequency. And that makes sense if you think about wavelength. If you have a long wavelength, not very many of them can go by every second. It's going to have low frequency. If you have a very short wavelength, the waves are really close together, you're going to have a whole lot of them go by every second. It'll have a high frequency. So then the only thing we haven't really talked about is going to be the amount of energy. Which one do you think would have high amounts of energy? The short wavelength here. If it has high frequency, a lot of them going by every second, it's also going to have high energy. And that makes it kind of easy for us to remember which ones go together. If we think about on the left-hand side, left has an L, it's long wavelength, low energy, and low frequency. All the L's go together. So on the left-hand side, long wavelength, low energy, low frequency. And you can see that the frequency measurement, that's the one that has the HZ in different ways. The prefix we put in front of it will change depending on what type of wave we're looking at. It starts with kilohertz, and then it keeps getting larger and larger, so we get mega, then giga, then tera, and we keep getting those larger prefixes in front of it. But we have our different types of waves that you saw in the Brain Pop video. We start out with radio waves with the longest wavelength. Then we get into FM radio and TV, radar. Microwaves are like what's in your microwave oven, cooking your food. Infrared, you can have infrared goggles where you can kind of pick up on heat in different places. Infrared is also what's used with your remotes whenever you turn on your TV or if we turn on the projector. And if you have a phone, you can put the camera on it, and whenever you look through your phone and the camera, you can actually, whenever you push buttons, see the infrared signal being transmitted. So here at the end of class, if you want to get out your phones and play with the remotes, you can. You can see that infrared. After infrared, we have this little section here that's kind of expanded. This little area is actually all of this right here. That's the visible light spectrum. That's what we can actually see. And it's made up of the colors of the rainbow. And the colors are labeled kind of funny on here. But can y'all think of a way, like in elementary school, that you learned how to remember the order of the colors? Roy, G, Biv. So in the visible spectrum, we're going to have the colors Roy, G, Biv. So red, orange, yellow, green, blue, indigo, violet. And that's the order according to the wavelength as well. Red will have the longest wavelength over here by 700 nanometers, and violet will have the shortest wavelength by 400 nanometers. But all of those colors fit into this little spot of our spectrum. That's the only part our eyes can pick up on. And it makes sense that right before red, right before our visible light spectrum starts, is when we would have infrared. So right after violet, we're going to have ultraviolet. So that's why it's called infrared and ultraviolet, is because infrared is right before red, ultraviolet's right after violet. And then we have our X-ray and gamma. And gamma will have the shortest wavelength that can go through the most things. And when we start doing some calculations, there's some formulas we can use. The speed of light is always going to be in meters per second, but the light that we see is in nanometers for the wavelength. So we need to be able to convert between those. So a nanometer is the same thing as 10 to the negative 9th meters. So if we had 700 nanometers, that would be 700 times 10 to the negative 9th meters. Okay. So we're going to look at something that looks very similar to this on the back. Only you're actually going to see the different wavelengths. You can see that the wavelength gets smaller as you move over to the right. And the pictures below kind of give you an idea of the size of that wavelength. So there at the beginning, the wavelengths are about the size of a building from the crest of one wave to the crest of the next. And then as you get down here to gamma, the atomic nuclei, that's how small it is from the top of one wave to the top of the next. So you can kind of see the range there of the size of these waves. There are only certain ones that you'll need to know on your test later on this week. You don't need to know all of them. They're on the front. These are the ones that you're going to need to know. And you'll need to kind of come up with where they're going to fall on our spectrum. So in the middle is what we can see. This is going to be our visible light. which is going to be made up of our colors, Roy G. Biv. And so then right before red, what do we have? Infrared. And then right after violet, we're going to have ultraviolet. So those are kind of the easiest ones to remember. What we can see is in the middle, and then we can figure out the infrared and ultraviolet from that. But then there's 4 more that we need to know. Do y'all remember what I said was the very smallest one? Gamma. So gamma is going to be here at the end, the smallest wavelength, shortest wavelength. And then X-ray is right there next to it. We know that X-rays can be harmful just like gamma rays can. They're going to be small enough they can get through a lot of things. On the other side, though, do y'all remember what the very largest wave is? Radio. And then we're going to have microwaves. And those are going to be the ones that are going to be on your test later on this week. And it's still going in the same order. Our long wavelength is on the left. These have low frequency. Not very many of them can go by every second because they have such a long wavelength, and they're going to have less energy in that wave as well. Now, there are some equations that we can use to relate these things to one another. The speed of a wave will always be constant, but we can relate the wavelength and the frequency to one another using this formula. The speed of light is equal to the frequency times the wavelength. The speed of light is always 3.00 times 10 to the 8th. So then the wavelength has to be in meters because this is in meters per second, and our frequency has to be in either seconds to the negative first or hertz. They're the same thing. So if we change one of these numbers, we can kind of see what it's going to do to the other. If I make my wavelength twice as long, then the frequency is going to be half as much because the wave's twice as big, half as many of them can go by every second. And we'll look at more examples like that here in a moment. Our second equation is going to relate energy to the frequency of our wave. And there was a guy named Max Planck who kind of found out the relationship between these. And if you divided the energy by the frequency, he came up with this constant value that we now use. Planck's constant is 6.63 times 10 to the negative 34th joule seconds. And if you just take the frequency and multiply times that, that'll give you the energy of that particle of light. Okay. And then our third equation is going to relate energy to wavelength. And for this one, it's kind of a combination of the others. You have to multiply Planck's constant times the speed of light, and then if you divide by the wavelength, we'll get the energy. And anytime you take a test, you'll be given all of these equations and all the constants. You won't have to memorize any of these. But for this one and the last equation, we're finding the energy of a photon. But we haven't talked about what a photon is. Does anyone know? It is a particle of light. Okay, we've been talking about light as a wave, but we saw in the brain pop video it can also be a stream of particles, which we call photons. We know that that prefix photo means light, a photograph, photosynthesis. Okay, anytime you have photo, it means light. So this is a small particle of light energy. So for these examples, we're just kind of saying if we change one thing in this way, how is that going to affect the other part of it? So if the frequency of a wave is doubled, what happens to the wave's energy? So which of our 3 equations, 1, 2, or 3, are we going to look at if we're dealing with frequency and energy? The second one. So if the frequency is doubled, if we take this and we multiply it times 2, what is that going to do to the energy over here on this side? It's also going to multiply it times 2. It's also going to double it. This is a direct relationship. Okay, since our variable is on 2 different sides of that equal sign, whatever I do to one, the other one will see that same impact. So it will be doubled. And if you also think about it, if your frequency is doubled, that means you have twice as many waves going by every second. And so the energy is going to be twice as much. Okay, For our next one, if the frequency of a wave is doubled, what happens to the wavelength? So which one has frequency and wavelength? The first one here. This time they're both on the same side. The speed of light is our constant value that cannot change. So if C has to stay the same, if I take frequency and multiply it times 2, what do I have to do to wavelength to kind of counteract that? Divide it by 2, or half, right? That's an inverse relationship. They're indirectly proportional. Whenever one increases, the other has to decrease. So it's halved. And again, think about it. If the frequency is doubled, you have twice as many waves going by every single second. In order for that to happen, the waves have to be half as big. Okay? If the wavelength of a wave is tripled, what happens to the wave's energy? So which one has wavelength and energy? Our third equation here. The wavelength is tripled. We take this thing and we multiply it times 3. We want to know what that does to the energy. If our wave is 3 times as big, is the energy going to increase or decrease? It's going to decrease. The longer wavelength is going to have less energy. How much is it going to decrease by? 3. It's a third. And that makes sense. We're dividing by 3 over here. So if this on the right-hand side is being divided by 3, we would also have to divide by 3 on that side. Okay. Last one here. If the wavelength of a wave is halved, what happens to the wave's frequency? So we're looking at the first one again. If the wavelength is cut in half, which we already show here, then our frequency has to double. Yeah. And again, just kind of think about it. If the wavelength's being cut in half, the wave is half as long, twice as many of them can go by every second, and they're half the distance. So the frequency doubles. So on your assignment, it's on the back of the worksheet that says electron configuration on the front. You should have already completed the front of this last week. We're on the back, and I'm going to go ahead and work the last one here with you. The retro questions are going to be extra credit. They can be +2 each if you want to do them. But we're going to go ahead and work the radio station one. For this one, you need to pick your favorite FM radio station. It can't be like XM radio or anything like that. So choose your favorite radio station and write down that frequency. I'm going to go with 102.1. So you write down your favorite radio station. And that frequency that you tune your radio to is actually in megahertz. And for us to use our formula, it has to be in hertz. So the way that we change that is by multiplying times 10 to the 6th. So you're just going to copy down your radio station in that second blank as well. That's not good scientific notation format, but it'll work for what we're trying to do. So if we have our frequency and we want to find the wavelength, we're trying to find out how long is that wave that's carrying your music to your car or to your radio. Okay, what equation do we want to use, the first, second, or third one? If we have frequency and we want to find wavelength. The first one. Our first one tells us the speed of light, c, is equal to the frequency of the wave times its wavelength. We've got to do a little bit of algebra. If we want to solve for the wavelength, what do we have to do with frequency? Well, what's going on between frequency and wavelength right now? They're being multiplied. So in order to undo that, we have to divide. So we're going to divide both sides by frequency. And when we do that on the right-hand side, the frequency will reduce out. It reduces to 1. So we've rearranged it for the wavelength, speed of light divided by frequency. And then we can just plug in our numbers. The speed of light will be the same for all of us. 3.00 times 10 to the 8th meters per second. Now that is in a vacuum. It'll be a slightly slower number whenever it's traveling through the air because of air resistance, but it's not very much that it's going to change. So we're just going to assume a perfect system where the speed of light is that value. And then our frequency will be whatever you came up with right there. So I'm going to fill in my radio station times 10 to the 6th. And instead of hertz, what's another unit we said we could use? Yeah, seconds to the negative first, which is the same is 1 over seconds, which is what we have right there. So those can cancel, and we'll be left with meters. Be sure whenever you put this into our calculators that we have, that that goes in parentheses. Otherwise, it won't divide correctly. When I divide mine, I get 2.94 meters. You should get somewhere around 3. Some of you will be a little bit above 3. Some of you will be a little bit below 3. But if you think about what a meter stick looks like, if you put 3 of those end to end, that would be the wavelength of that wave carrying that music to your radio, from the top of one wave to the next. So it's a pretty large wave carrying that signal. We're going to go ahead and look at the top real quick, and then I'll come and help anyone who needs help with their calculations. So let's go ahead and look at the top real quick. When you're trying to work the rest of this, you're just going to use that first spectrum that was on our set of notes. So the very first page of our set of notes had this picture right here. And this is what we're going to look at in order to figure out, does something have more energy? Does something have a greater wavelength? Things like that. So our first question asks us, which one is going to have more energy, or which one has less energy than yellow? So if you've got your colors, Roy G. Biv, and it looks a little bit different on yours. Yellow's right here, and lower energy is going to be to the left, higher energy on the right. So you want anything that's going to be there in front of it. So you could put red and orange, or on your paper it says red and what? Crimson. Okay. If we look at number 6, which radiation has the longer wavelength? Which side has longer wavelength, left or right? Left has the longer wavelength. This one has a shorter wavelength. So if we want to know the longer wavelength between X-rays and infrared, we just find both of them. We've got infrared right over here before red. We've got X-rays over here. So which one has a longer wavelength between X-rays and infrared? Infrared. So use your notes, use that picture that's on the first page of your notes, and just kind of choose which one would have more or less, whatever it is it's asking of you.